And the recording is started, so the floor is yours.
Okay, so thank you very much for coming and for the invitation to give this talk. I'm really happy to talk to you about my work I've been doing in the last year and a half, one could say. So it's a confinement joint work with Federico Castillo, Julia Libat, Arnaud Padrol, Eva Philippe, and Christian Schilling. And it essentially goes like this. So the story, just that we're going to see a little bit more during the talk, but the story is that there is some problem in quantum physics, more specifically about elementary particles, that it turns out that problem requires some discrete geometry to be solved. And this needed to introduce the notion of line-up polytopes, which is not completely new, but is a new type of polytope that now has an application in physics and is related to symmetric polytopes, matroids, and things like this. So that's going to be today's goal of the talk, to essentially introduce them, but maybe we're not going to go too much into details about what they are, but we're going to see them at the very end. Okay. So here's the menu for today. Since for online talks nowadays, so the attention span tends to actually decrease exponentially with time. So I thought maybe I start with very quick takeaway messages for the talk in actually a hierarchy. So like going from less formal to a little bit more formal and then to technical. So like everyone, I think, depending on your background, will be able to enjoy the takeaway message. And then we're going to get into the talk about the representability problem, Pauli's exclusion principle, and then introduce line-up polytopes at the end for a convex relaxation of this representability problem in physics. And then at the very end, we're going to have an outlook about potential further research about discrete geometry in physics together. Okay, so let's start. And now I will just give you the elevator pitch. So just like 1 minute or two. And let's just imagine that we're sitting at a bar drinking a beer. This would be the way that I would explain what we did. So you all probably know the Roadrunner and the Coyote. And the Coyote is looking for the Roadrunner and wants to eat it, and often just like hits a wall. Okay, so that's a demonstration of a very well-known physical law, is that if you want to pass through a wall, you're going to get hurt. Okay, so that's a very deep physical law. You cannot pass through a wall. Okay, so the takeaway of the talk is that we find new mathematical rules, so phrased, let's say, abstractly, that should be satisfied by certain systems of elementary particles. So you can imagine Coyote is made out of, I don't know, billions of electrons and neutrons and stuff like that. And so that is a system of elementary particles. And this system has to obey certain mathematical rules. Okay, and so we find new mathematical rules that can then be tested in real life with real world material. And I say should here because it's not been tested yet, but that is essentially the goal of this project. Okay, so that's what we do. Now let's go a little bit deeper. So let's now imagine that I have a little bit more time and we're walking together to go to the cafeteria for lunch. And so what I would start with is the periodic table that likely you've seen in your chemistry or your physics class in high school or college. And it looks somehow like the first picture on the left here. And I chose that picture because it has some kind of combinatorial flavor to it. There's like blocks that you see here with different letters and numbers. And these blocks describe properties that the electrons that gravitate around the nucleus should have. So these quantum states are composed by 4 quantum numbers. If you're a mathematician, you can just imagine like invariants. So like 4 quantities that describe entirely the particle, so each electron in the atom. So for example, on the first row of the table, we see one S. Okay, so the one here is the principal quantum number. Okay, so it's a non-negative integer. Okay, so it goes like 1, 2, 3, 4, 5, 6, 7, etc. And the second number is the azimuthal number, which is a letter. So S, P, D, and F. And maybe you've seen these kind of shapes of orbitals. That's a little bit what they describe. And in each shape, you can have a certain specific number of electrons. So for example, in 1s, you can have at most 2 electrons, the one here for hydrogen, and then the second electron would then complete the first shell to get helium right here on top. Okay, and then it continues like this. So you see that 2s can also have 2 electrons, and then 2p can have, what is it, 6, and it continues like this. And then if you're a combinatorialist, you notice, okay, so I don't see a p, a 1p, for example. That's because to get the second azimuthal number, you have to wait until the second principal number. So there are dependencies between the numbers. They're not completely independent. Okay, so there are interdependence between principal, azimuthal, magnetic, and spin. So magnetic and spin are not represented here, but they have dependencies. Okay, and this is organized like this. And the reason for that is a well-known principle that we're going to see on the next slide. And here on this picture, we essentially see that, you know, when we learn about chemistry, you learn about the ground state, so the lowest energy that let's say an atom of helium can have, or like an atom of carbon, whatever. And then like a pretty typical question in an exam in chemistry would be like, okay, please fill, you know, the orbitals. And then like it says, okay, you have 8 electrons, now fill it to the second level of energy, and so on and so forth. And then it has to follow this, in German, Aufbau principle, that essentially this dictates the level of energy of each orbital. And then it has to be filled according to the arrows here that are depicted. Okay. Okay, so that now we're pretty close to the cafeteria. Now I have to get the point. So the first picture, essentially, I don't want to say is a consequence of only the Pauli exclusion principle, but definitely Pauli exclusion principle contributes to this. That says that no 2 electrons, or in general fermions, can occupy at the same time the same quantum state. Okay, and so that's the more complicated way to say that the coyote cannot pass through the wall. It's like at the same time, you cannot have 2 electrons that are at the same place in space. Okay, so that's the, let's say, the complicated way to phrase this. And then the Aufbau principle says that in the ground state, you can think at 0 temperature, at 0 Kelvin, electrons fill subshells of the lowest available energy, and then you start filling subshells of higher energy, and so on. That's the Aufbau principle. And then the takeaway message is now that we formulate exclusion principles that generalize that of Pauli's exclusion principle. And these principles take the form of linear inequalities. Okay, so now we're getting a little bit more into geometry. These principles take the form of linear inequalities that, here comes a big chunk, eigenvalues of operators representing excited quantum systems must satisfy. So now we're looking not at the ground state, but a quantum system that has some energy, that has like a mixture of states. And then there are like operators representing this state, and then these operators have eigenvalues, and then we give linear inequalities that these eigenvalues must satisfy. Okay, so this is the takeaway message. If you are familiar with linear inequalities, then it means that there is some kind of polytope behind right there. Okay, line of polytopes, essentially describing that. Okay, now for the more, let's say, caffeinated version of the takeaway message. So people that know about my research, I study symmetric polytopes. So for example, the permutahedron, the hypersimplex, And these symmetric polytopes have a lot of combinatorial structure behind. So here the permutahedron is related to the symmetric group. And here, for example, the hypersimplex is related to matroids, for example, in particular. Okay, so these are objects that I study. And then the problem that came about is, imagine that I look at the permutahedron. The permutahedron is obtained by taking one point. Typically, you say, take 1, 2, 3, 4, 5, 6, 7, up to D, that vector, and now permute the coordinates, and then take the convex hull. Then you will get the permutahedron, which is here depicted on the left. Perfect. Now, what happens if you take 2 points? I don't know. Let's say in dimension 4, 1, 2, 3, 4, and 1, 2, 3, 5. These 2 points. And then you spin both of them. You get 2 different permutahedra. And now you take the union as sets. And you take the convex hull. And the question is, as a discrete geometer, what is the H description of this new thing? This hasn't been done yet. I mean, now we have looked at this problem and we gave a solution in our research project. And this is what this talk is about. It's about some generalizations of symmetric polytopes. And so here's the overview, the point. So the fact is that we can actually formulate Pauli's exclusion principle entirely using discrete geometry. And so this seems to be a fact that was that escaped the community of discrete geometry. The following fact, that the expected number of particles in each orbital of a quantum system does not exceed 1. So if you look in a probabilistic way to a quantum state and you have a bunch of possible orbitals, the Pauli exclusion principle says you cannot see 2 particles at the same time in the same place. So if you look at the expected value of a specific orbital to appear, it has to be smaller or equal to 1. And so it turns out that the possible expected numbers, when you look at them all together, this set of expected numbers form a convex set, a polytope, and it's the hypersimplex. Actually, the hypersimplex is an equivalent, let's say, formulation of the Pauli exclusion principle. And we're going to see this. And what we do is that we formulate generalized exclusion principles that take the following form: the convex hull of unions of certain symmetric polytopes, okay, given to you in a certain way, uncover restrictions on the expected number of particles in each orbital, now of mixtures of excited states of a quantum system. So it's a bit complicated. We're going to see what it is. And now the takeaway of the talk is we introduce polytopes that generalize the permutahedra and describe their representations and combinatorial structure. These polytopes relate to several well-studied objects, for example, moment polytopes, shifted complexes, Grassmannians, and many others. Okay, so here's 2 examples. So there are 2 types of particles in life. They're fermions and bosons. And so those are 2 line-up polytopes that you can obtain, that we can describe. So here would be a line-up polytope that corresponds to fermions. So here you see, for example, 2 particles in 4 orbitals. So 4 orbitals means like the 4 places where a 1 can be. And you have 2 particles, so they have to be somewhere. And in between, inside of this polytope, they represent kind of intermediate positions that you can be between 2 observations. Okay, and the line-up polytope is then contained in the hypersimplex here. And for bosons, it's a little bit a different scenario. There's no Pauli exclusion principle, so they can pile up on top of each other. And so now, instead of having the hypersimplex, you have the simplex, and then you obtain such a symmetric polytope. Okay, so who is we in the last 3 takeaway messages? So this work has been done with Federico, Julia, Arnaud, Eva, and Christian. So Christian came to me with an email about this question about polytopes. And later then Julia explained the foundations of reduced, what is it? I have to say it properly, it's an acronym. Reduced density matrix functional theory. So that's something in physics. And she has been working out the details of this theory that relies on line-up polytopes. And it turns out that these line-up polytopes are a certain, let's say, extension of the work of Eva and Arnaud about sweep polytopes, something that they've been also working on this year. And so we've been working together in order to establish this theory. And so Federico at this time was in Leipzig, now he's in Chile, and Julia and Kristen are in Munich, and Arnaud and Eva are in Paris. Okay. So before we start, we have to set the table. So I'm going to give you a crash course in quantum mechanics. So again, just a disclaimer, I'm not a physicist, so there can be certain mistakes here. I apologize already in advance if there are. But I'm just going to give you my take of what it takes to understand what's going on. Okay, so in quantum mechanics, there are like 3 postulates, the first 3, that we will need to understand a little bit. So classically, physical quantities like temperature, energy, position, momenta, things like this, become positive semi-definite Hermitian operators, for example, the Hamiltonian, in the quantum world. Okay, and then typically physicists refer to this as observables. Okay, so these, because this is a long name, then you call it an observable, and that's way shorter. And then Newton, in order to describe an apple, he would arrive and tell you where it is and where it's going. Okay, so you need 6 variables in order to describe, let's say, completely something, an object in space. Okay, and this thing then becomes, in the quantum world, a unit vector in the state space. So some space, that's called the state space, that describes every single state that a particle can be in, let's say orbitals and whatnot. And this is usually denoted by a wave function. And lastly, the postulate number 3 says that when you're going into the lab and you're measuring a physical quantity, this physical quantity has to be one of the eigenvalues of the corresponding observable, which is an operator. If the word operator scares you, just think matrix. So the eigenvalues of these matrices are the possible measures that you're going to take on this object. Okay, now we continue, so a little bit more concrete. So we're going to denote by H a d-dimensional Hilbert space that is a complex vector space equipped with a sesquilinear product. So it is essentially just conjugating, instead of taking the usual inner product, you just conjugate one of the 2 components. And on that space, we will look at bounded Hermitian operators. Those are like the matrices whose conjugate transposes itself. Okay, so it means that the diagonal has to consist of real numbers. And that set forms a real Euclidean space with an inner product, which is given by taking the trace of the product of the 2 matrices. Okay, and then we're going to look at a subset of these operators, those that are positive semi-definite Hermitian operators, typically denoted by rho. And because we want to give them a probabilistic meaning, we want that the eigenvalues sum up to 1. So the trace is equal to 1. And we call these things density operators. Okay, so those are these observables here. Okay, so those are matrices. And so it means that eigenvalues of density operators are used to describe physical quantities. Okay. Now, since I'm a geometer, right there, I noted that if you look at the set of density operators, that is a convex set in the set of bounded Hermitian operators. Because if you take a convex combination of those, you will remain positive semi-definite and you will remain Hermitian. Okay. And then it means that the eigenvalues of density operators, they have to be included in the interval 0, 1. So now we're starting to see a little bit of discrete geometry right here, because it means that if I take a point in the regular d-1 simplex, this then corresponds to an ordered spectra of a density operator. Okay, so that's going to be important later. So there is essentially a labeling of all the density operators by points inside of a polytope, the simplex. Great. Now, each electron that you're going to look at has its associated Hilbert space to denote the state it can be in. And now let's say that you're studying maybe an atom, a big atom, or like a molecule, or maybe a virus. It has a lot and a lot and a lot, like thousands of atoms, and maybe like of molecules. So in order to study such a big system, you have to take the tensor product of these one particle Hilbert spaces. Okay, and I'm going to denote this shorthand by Hn. And so Hn is going to just be a tensor of these Hilbert spaces altogether. And since we're doing physics but not math, it turns out that the states that we're going to study obey certain exchange symmetries. So if we're looking at fermions, it turns out that if you exchange two fermions, the state has to be anti-symmetric. So the sign has to change by -1 if you interchange two fermions. And so we're going to only look at that subspace here, which is anti-symmetric. Okay, and so if you then deal with bosons, it is different. This time, actually, when you interchange two bosons, nothing changes. It has to remain exactly the same state. Okay, and the amazing consequence here is that this gives birth to a really rich interplay between, let's say, algebraic combinatorics and quantum physics. There are journals dedicated to this, and their representation of the symmetric group and symmetric functions are really important to understand in order to understand also these big state space. Okay, so these are the spaces that we're going to work with. And the big idea of quantum mechanics then is to use H to parameterize the states of a particle, and density operators to parameterize physical quantities or observables that can be measured. Okay, but unfortunately, we're not living in a finite dimensional space. Okay, so like the world we live in, it has to be taken to be infinite dimensional. And so when you're a theoretical physicist, in order for results to be testable, you need to consider or to think about what happens if you push the dimension, the small d, to infinity. Okay, so theorists consider finite dimensional Hilbert spaces, but seek mathematical results that generalize when taking the limit at infinity. So that's also important. Okay, so now we are ready to start with my take of the N-Representability problem. So I've talked about the Pauli exclusion principle that was formulated in 1925 that says that, okay, two electrons cannot be in the same place at the same time. Perfect. A little bit later, Dirac and von Neumann gave this really deep mathematical framework to deal with quantum mechanics. So the book of von Neumann is still nowadays used to understand what quantum mechanics is about. And Dirac introduced density matrices to deal with mixed states. So what happens, for example, when you're transitioning from one state to another? Okay, so here's how you go from a wave function to a density matrix. So here, if you followed carefully, you should interject and say, wait a minute, a state is supposed to be a unit vector in the Hilbert space, and now you're going to say that a density matrix, which was representing an observable, is a state. So here's how you do it. So the recipe is, let's imagine that we have a system that we know entirely, that's described by a wave function that corresponds to a certain, because you know completely this system, that corresponds to a unit vector in the state space, V, that describes this psi. And so you have a vector here, which is a unit vector. And whenever you have a unit vector, you can always create a matrix that's the projector. So the transformation that projects everything to that vector and projects the orthogonal complement to the origin. So if you're scared of this notation, just think it's a column vector multiplied with a row vector, and that gives you a matrix. Okay, so that's a transformation. And then the matrix of this turns out to be positive, semi-definite, Hermitian, and has trace 1. So you have a density matrix row that describes a state. Okay, and the cool thing about this is that it allows to deal with mixed states. Okay, so you can actually consider states that could be like maybe half chances are that it is in this state and the other half is in another state. And so you can mix them like this. So you can take convex combinations of states like that. Okay, some time after that, so Watanabe and Usimi are Japanese physicists. And so Watanabe formulated a necessary spectral condition on density matrices to fulfill Pauli's exclusion principle. And he did that while he was visiting Eisenberg in Leipzig. And Usimi introduced the notion of reduced density matrices. And so we're going to talk about this next. So imagine again that you're dealing with a huge molecule and you want to study it. That's a huge space because you took the tensor of, let's say, a huge Hilbert space, and that's a really, really, really complicated thing. So the idea here is to reduce that density matrix to something smaller, okay, and then study the image of a certain map. So you're going to project your matrix to something smaller and see what you get. And so imagine that you have two particles, P and Q, with their one particle Hilbert spaces, okay? So you have this tensor here, and here you have the set of matrices on that space, so that acts on that space. The partial trace will take that tensor and return to you a matrix that acts on just one particle, okay? And this is like the, let's say, abstract way to define the partial trace is that if you write a basis of this space, it is written in terms of these kind of blocks here. And the recipe is that you take this block and then you trace out, that's what the physicists call, is that you trace out this piece here that's inside of this HQ. You trace it out, it becomes a scalar, and then you multiply it with the corresponding endomorphism, rho cross rho star. And of course, then you can do this with any number of particles. So here's the way to define it for 2, but you can do it for n particles. And you don't have to partial trace to just one element, but you can partial trace to 2, 3, 4, 5, and whatever. And then the idea is to try to use the image to work. Okay, so the question is, what is the image of that linear map? Okay, so this, if you're teaching linear algebra, that's a wonderful thing to look at. So let's say linear algebra 2 or 3, partial trace is really an amazing construction. Okay, so here's a visualization of this. So here, I said previously that the set of density operators on n particles is a convex set, so a beautiful round object like this, let's say. And then you take the partial trace. So on the right-hand side, you have the density operators on only one particle. And you see that not everything is attained. So it's not surjective. So it's not a surjective function. You need to characterize what's in the image of this map, okay? And there's stuff that's exposed, there's stuff that's not exposed. And so that is the idea of why you want to use reduced density matrices. For example, Coulson arrived a little bit later and had a vision. Because the wave function is really complicated, And it's really hard to solve. So you have like differential equations that you have to solve with a lot of variables. That's really difficult. So his vision was to replace it with these matrices. Beautiful matrices, linear algebra should do the thing. So 1 and 2 RDMs. But for that, you need an efficient method to characterize the image. That is literally the N-Representability problem. And the really cool thing is that's a linear algebra question, essentially. Okay. Then comes a Canadian mathematician, Coleman, in the 60s. And so Coleman is more known, I would say, maybe in the quantum chemistry world, but he's a mathematician. And he entered Princeton at the same time as Feynman, the same year. And actually, the famous picture of Dirac and Feynman during a meeting, I think in the 70s, was taken by Coleman himself. So that famous photograph. And so what Coleman did was to characterize the spectra of those 1 RDMs, so those reduced density matrices that are N-representable. So he did characterize the image using the spectra. And he said, well, the Pauli exclusion principle turns out to have an interpretation that goes as follows. So imagine that you take a density matrix that represents n particles. You take the partial trace, you will obtain a density matrix that is for a one that is inside of the 1 particle system state space, and it will have certain eigenvalues, and you know they have to sum up to 1. So that condition is there already. And then the condition that was added, that's necessary and sufficient, it says that all the eigenvalues must be between 0 and 1 over n. Okay, so inside of the simplex that I mentioned before, where anything can happen, now you cannot be too big. One of the coordinates cannot be, like all the coordinates cannot be too large. Okay, so they're bounded above by 1 over n, the number of particles that you started with. And the really big problem is then, what about if I restrict the starting set to have a certain spectra? Okay, so that's the really big question. But before we proceed, here, the discrete geometers in the audience should look at these inequalities and notice something interesting. It's actually the H description of hypersimplices. Okay, so the Pauli exclusion principle by a theorem of Coleman has a geometric interpretation. Okay, so here again, the visualization, we start with a bunch of huge tensors. We take partial traces, we obtain matrices here, and only a subset is attained. And then what Coleman did was he took that set, looked at the spectra, and obtained the following blue polytope. Okay, so in red, you have all the possible spectra, right? So that's a simplex. But those that are possible to be obtained from a system of n particles, they have to be mapped to this hypersimplex here. Okay, and now if you actually restrict to spectra that are decreasing, you get this purple fundamental domain. Okay, so you can also restrict to that set if you like. Okay, so what is the idea behind Coulson's vision? As you probably know, nature always wants to minimize entropy. So when you're going to observe things, or like make an observation in the lab, the thing that you're going to observe is likely going to be an extremum of certain function of the Hamiltonian and things like that. So because the energy, for example, is a linear function in the 1 and 2 body distribution function, the variational minimum, the thing you're going to observe, will lie on the boundary determined by the N-representability condition. So if you are to work with something here, and that's the thing you want to obtain, right? So you want the description of your state. Actually, the way to go is to go backwards, to start here by looking what's at the boundary of this polytope, and then go backwards. Okay, go back and reconstruct a starting first good guess for your optimization. Okay, and so that is the idea behind Coulson's vision. And then what Coleman did was that he took here the state space, the density operators, he took the partial trace, then looked at the spectra, and it turns out that that's a scaled version of the hypersimplex. Okay, and so that fact escaped totally the discrete geometry community. Okay, so here I want to go back to the infinite limit. So he said that a one particle density matrix is N-representable if and only if each eigenvalue is between 0 and 1 over n, and the total sum is 1. And the really cool thing here is that the dimension of the Hilbert space that you used is essentially absent from the previous sentence. So if you would have done it with 10 orbitals or 1,000,000, that statement would have been the same. Therefore, that statement can be tested in labs. And so far, after almost 100 years, Pauli's exclusion principle has not been disproved. Okay, so now here's the physical interpretation of these eigenvalues. So now if you scale the trace to n, so you multiply these eigenvalues by n, the eigenvalues then represent the average number of particles in each orbitals that the atom can be in. So the occupation numbers do not exceed 1, because if you take 1 divided by n multiplied by n, the eigenvalues cannot exceed 1. So that bears witness to Pauli's exclusion principle. Okay, so that's just to show what the hypersimplex means here. Okay, so now the big millennium problem is, maybe not millennium problem, maybe I shouldn't call it this way, but like the problem that was there for a very long time is, what if instead of considering all of the density operators, I only look at those that have a specific spectra W. Then I take the partial trace and then I look at the spectrum of these matrices. What is the image? It turns out that this is really hard. So from the 1960s all the way to the almost to the end of the century, there was almost no progress whatsoever about this question. Okay, until Klyachko, so a Russian mathematician, gave a solution to another problem, Weil's problem, about Hermitian operators. And he gave a polytopal description that we're going to see of this set here. Okay, and his characterization relies on the foundational work of Atiyah, Gilmian, Steinberg, Constant, Kirwan, Bernstein, and Jamar in symplectic geometry and representation theory. And these are really massive mathematical landmarks. So Klyachko himself, having done a massive work, was also essentially standing on the shoulder of giants and really massive results. So that's no wonder that it took 40 years to get the solution, because it relied on really deep mathematical results. Okay, so here's a tiny problem for physicists. Although the problem is essentially solved, the solution is not really useful in practice. And so we want to seek something that we can use, that physicists can use. And so now we can come to the main dish of today. So if you're lost, now is the time to come back. Okay, so here's a really beautiful result. Now consider a set of matrices, so D by D Hermitian matrices. So you have a bunch of complex matrices whose spectrum is equal to W. So again, a vector of weights, and the entries are decreasing, let's say, and they sum up to 1. So we know what the spectrum is, and they are Hermitian, so their conjugate transpose is equal to themselves. That's a set of matrices. Good. Now take that set of matrices and forget about everything but the diagonal. Just care about the diagonal and write this in vectors. Well, it turns out that the image of this map, of this projection map to the diagonal, the image is the permutahedra. So only specifying the spectra of Hermitian matrices and taking the diagonal, somehow, amazingly, that image is the permutahedra. So you will take this vector W, you will permute all the entries, let's say like 0.1, 0.2, 0.3, and 0.4, that sums to 1. You permute these entries, you get a typical permutahedra, and every single point inside of that permutahedra represent a certain diagonal of an Hermitian matrix with that specific spectra. That's an amazing result. So that was first proof in one direction by Schur, and then Horn 50 years later, at the middle of the 20th century, proved the converse. So that's a beautiful result, I find. And now the constraint formalism of Klyachko can be formulated this way. So now, instead of considering all the density operators, all of the density matrices, just consider those that have spectrum W. Okay, it turns out that this set is not convex, meaning it's difficult, but it is still nice enough. It is a unitary orbit. So if you change basis orthogonally, you're still in the same set. It admits a symplectic structure. And when you take the partial trace, the result is also unitary invariant, which means that Klyachko could use a spectral characterization. And that's what he did 40 years later. So in 2006, Klyachko looked at that set of density operators. That's a set of matrices. He projected that to a smaller set. And he said that an operator is in the image if, when you look at the spectrum and you order it decreasingly, it belongs to a certain polytope that I denote by pi n dw. So it depends on n, the number of particles, the dimension of the Hilbert space, and the weights. Okay. And now the practical problem is that the dependence on D here is too big, is really non-trivial. And so in practice, so far, that polytope only has been determined up to 5 fermions and 10 orbitals. So you can only deal with like the first 2 rows of the periodic table. You cannot deal with molecules, anything in practice. Okay. So even though you have a description of a polytope, you cannot really use it. Okay, so the approach that we use stems from the theory of ensemble, reduced density matrices functional theory for excited states. And this led to a hierarchical generalization of Pauli's exclusion principle. And so this is described in the pioneer work of Christian Schilling and Stefano Pitalis that was published this year in the Physics Review Letters. And the idea is, instead of taking the spectra, you choose a basis and you do as Schur-Hahn, you just take the diagonal. Instead of taking spectra, like Klyachko did, you just take the diagonal operation instead. And by Schur-Hahn, the result here is the convex hull of the symmetrization. Okay, so here's a picture, schematic picture of the idea. Here's a polytope that's often referred as a rosace in the literature. It has like a curved boundary because you can imagine there's tons and tons and tons of facets, and they're hard to obtain. You have to use symplectic geometry, representation theory, and so on, just to obtain a few facets. And there's tons of them. So now the idea is you spin that petal, you obtain a beautiful yellow flower, you take the convex hull, and so you get a bigger set. But it turns out that that bigger set is a polytope that's easy to describe. And then you can restrict to the decrease to the fundamental domain. And now you get an approximation of Klyachko's polytope. And it turns out that the new inequalities here are useful in physics. Okay, so here's an explicit example for 4 orbitals and 2 particles, something I can draw because in higher dimensions we can't. So this is the hypersimplex in blue. This is Coleman's result that says Pauli's exclusion principle says you have to be contained in the hypersimplex in blue. And then Klyachko says that the solution is the green polytope here, right in the middle, right there. Well, the description that we give is take this green polytope, take its orbit under the action of the symmetric group, and then take the convex hull. You get a larger polytope, which in this case is a type B permutahedra. And those inequalities are useful directly for this RDMFT theory. Okay, and so this is what we do. We describe these red polytopes. And now the question, just to finish in the last 5 to 10 minutes, how to get that polytope, this red polytope. And then this is where we introduce lineup polytopes. So now, imagine that you have a point configuration in R to the D, in very general. So forget a little bit about our problem, just look at a bunch of points in R to the D, and I define the following thing. I call a lineup an ordered sequence of R largest points with respect to a generic linear functional. Okay, so here's 6 points on the plane. So the linear functional, let's say, is optimizing towards the left. So E is going to have the largest value. So E comes first. Then you scan A, and then you find B. Okay, so EAB is a 3 lineup of this point configuration. But FAD cannot be a 3 lineup because there will be, in any way that you're going to try to scan the points, if you start with 6, you know that you kind of have to be like a line somehow in this direction. And then you have to scan A. But if you scan F, then A, there's no way you can scan D without scanning C first, because C is in the convex hull. Okay, so this is not a lineup. And now the question is, given a certain point configuration, how do you obtain all the lineups? Well, this is what we answer. So in the physics context, the example that's relevant is when we take vertices of the hypersimplex ND, representing the Pauli exclusion principle. The vertices, they correspond to all the possible ways that you can put electrons or fermions in d orbitals, right? Because you have d slots, you have d dimensions, and now you want to put n fermions in these. So you put ones and zeros, and so those are exactly the vertices of the hypersimplex. And now the question is, how do you obtain all the lineups? Okay, so here for n is equal to 4, we use the Gale order. Okay, so this is where the matroids come into play. That lineups then correspond to certain saturated chains of order ideals. So we can use combinatorics. So this is really, really easy to implement in the computer. And then in order to check whether a saturated chain of order ideals corresponds to a lineup, we have to check a certain linear program. And if a linear program has a solution, then we get a lineup. And so the idea is we can use combinatorics and geometry to get all the lineups. And here's the main theorem now of the talk. If you have a point configuration V and you're interested in figuring out all the R lineups of V, then there exists a polytope whose vertices are in bijection with the R lineups, and the open normal cones of these vertices give you precisely the linear functional inducing each and every R lineups. Okay, so here's the example. So here you would have these sequence of weights that help you build this red polytope. And you have the hypersimplex here. You take the R lineups of this with weights W, and that is exactly equal to the symmetrization of the Klyachko's polytope. So here's Klyachko's polytope. You act by the symmetric group. You take the convex hull, and this is a lineup polytope. Okay, so essentially we can give a really easy answer to this problem using combinatorics and geometry. Okay, so here's the V representation of the polytope. As I said, you can obtain it using the lineups. For each and every lineup that you can obtain, you take the convex hull of these points here. So for every linear functional that you can use, you get a lineup, and then you put the lineup that you obtain, and you put it with this ponderation, this weighted sum, and then you take the convex hull, and it turns out that this gives you the lineup polytope. And for physicists, you need to obtain the H representation. So what we did in our project is obtain an H representation. You obtain an H representation of this polytope, and what we did was obtaining a fast algorithm for symmetric polytopes, and we obtained the general description. Okay, so now just for dessert, just to finish off, here's a few consequences and a bit of outlook. So for any given R, so the length of the lineup, the inequalities stabilize. So this means that we can increase the number of particles and the number of orbitals to infinity, which then lead to new exclusion principles through linear inequalities. We computed many of them. And even though this polytope is more simple, it is still physically relevant. It also extends, as I've mentioned, the theory of sweep polytopes that Eva and Arnaud have presented earlier this year. And finally, this polytope has a lot of properties. It is symmetric. It is a moment polytope, a fiber polytope, and has many other properties. And then there are possible extensions to quantum information theory of qubits. And so there's also a lot of work to be done later this year. And so with that, I will conclude. So thank you very much for your attention. And if you have questions, then I can answer them. Thank you.
All right. Thank you very much. Do we have any questions from the audience? That does not seem to be the case. In that case, yeah, thanks again.
Thank you
For your nice talk.
What do the semiknödel have to do with this?
So this, I mean, because you've probably noticed the theme of the talk was very much related to food. So I visited the group of Christian Schilling and Julia Liebert this fall in Munich. And actually we did an excursion, like a one-day excursion at Tegernsee in the south. And that was like a nice conclusion to the project. And that's the Semiknödel that I had right next to the lake. So that's a really beautiful, really nice beer garden on top of the mountain there with a view. And so that was the conclusion of the project this year, actually like a month ago. Yeah.
It does look very delicious.
Yeah, it was really, really good. Yeah.
Yeah, do we have any other questions? I don't think so. So yes, I will